Alright, 7.5 exponential and logarithmic models. Alright, so there are about 5 basic types of these that we're going to be going over in this section. This first slide and this next slide will be just a general overview, and then we'll dive a little deeper at the end of this video. So first and second one, hopefully you've seen before. Then after that, some newer, newish models that you may or may not have seen before. The first two you should have. They're the exponential growth and exponential decay. So whenever we have anything with a base to a power, if the x variable is positive, it's going to be growth. It's going to be decay if it's negative up here. Okay. Growth is, as you can tell, when x increases, y increases, right? And then with decay, as x increases, y decreases. Okay. It's exponential because as x increases, it gets really, really big. Okay. And it grows really, really fast. So that's why it's called exponential growth and decay. Down here, 3 and 4 are some of your newer ones. Number 3, it's Gaussian. It's of the format y equals a times e to the power of negative parenthesis x minus b to the power of 2 divided by c. So anything that's of that form with an x squared to the exponent, that is, with a base, that is going to be Gaussian. And your graph would look something like this. Okay, so it's increasing, then the original function, whenever it's at x equals 0, that starts decreasing again. So it's like y equals e to the power of negative x squared. And 4. I did not write the name here. I better do that. 4 is called the logistic model. Logistic model is whenever it's increasing and then slowly stops increasing because there is a limit as to what it be. And it's of the format y equals a over 1 plus b base e to the power of negative rx, where a is greater than 0. Because a needs to be greater than 0 because it's a limit. Okay, so it's going to be a positive limit. You can only have so many of whatever that value is. Maybe you're talking about an apartment complex where you can only have so many people in it, right? You can only fit so many people in an apartment complex, right, or something along those lines. So that would be a limit. Or if you have a fish tank, right? So you can reasonably only fit so many fish in your fish tank, right? And that would be your limit up there as to how many you would have. This R is just the rate. That's all that basically means. So this example right here, 3 is the limit right here, and it's over 1 plus e to the power of negative 5x. So it's not going to reach 3. Okay, it's never going to go past 3, but it's going to keep creeping up closer and closer. Now we have the natural log model and the common log model. So it's pretty much what it is. Natural log model, ln x, common log model, y equals log x with the base 10. I wrote the standard form of it, which is y equals a plus b ln x, and y equals a plus b log x. If you notice the difference between these graphs, you'll notice that this is increased a little faster than this one. Why is that? Remember, this is base e and this is base 10. E is about 2.71, so yeah, it's going to increase a little faster because of that. And when we talk about logarithms, as opposed to base 10, which slowly increases till we hit later. Okay. All right. So first example we'll be doing is an exponential growth and decay model. So there's a lot of different examples we can do with these 5 types of graphs and functions. We won't be able to do every single possible. We'll give you a few to get you an idea. Number 40 in your book on page 516. Okay, I'm not going to do all of 40 because it's going to take a minute, and we'll finish the rest in class. But what it's saying is it gives us a table of 5 different countries with the population in 2000 and 2015. Let's focus for this case Bulgaria. had a population of 7.8 million in 2000, and in 2015 it had a population of 6.9 million. Now, once to find the exponential growth or decay model, if we consider that 2000 is year zero, okay? Since 2000 is year zero, this is our A value for our exponential growth decay. Exponential growth decay is, remember, of the form y equals a base e to the power of bx. So if 7.8 are starting, then 7.8 is going to be our A. I don't know what B is yet. That's what we need to find in order to solve. Okay, that's our goal. Okay, so whenever we hit 2015, the output's 6.9 million. So the output is 6.9 million, and then the x, your input, will be 15, because that's how many years have passed since year 2000. Okay, we need to solve for B. So we divide both sides by 7.8, giving our left side a 0.88, approximately. Okay, that's rounded, but go with it for now. Base e to the power of 15b. In order to solve, I need to find the ln of both sides. Okay, ln of 0.88 is negative 0.123 approximately, equals 15b. Divide both sides by 15, and you'll get our b value to be negative 0.00, we'll say 82. We'll stop rounding it there. So what's our answer then? Your exponential, well, in this case it's decay because your b value is negative. Your exponential decay is going to be y equals 7.8 base e to the power of negative 0.0082x. That is your answer. Alright, next example, the Gaussian model. So we have this function right here. If you go to page 518, number 53, you'll see this model here representing IQ scores. And the IQ scores range from 70 to 115. They want us to find the average IQ score. Okay. Also, make note, it also wants us to use a graphing utility for part 1, or graphing calculator, as we would like to say. So go ahead and punch that in your calculator. Whenever you use your calculator, a few things to note. Keep in mind your x values are between here, right? So you need to change your window so that it includes these values. Maybe a little less than 70 and a little bit more than 115. Alright, so let's look at the initial term. So they're going to be really small numbers, so your window of outputs between negative 10 and 10, you're probably not going to be able to see the graph. So it might be a better idea to make it between 0 and 1, and start with there and see if you see anything, and then adjust from there. So after you use the second trace max feature, because that's what you want to find, the max is going to tell you what the average IQ score. And when you do that, you'll get approximately 100 is the average IQ score. If you have issues trying to graph that, ask me in class. I'll be happy to show you. So this is number 55 on page 518, used by the function y equals right here. And it's to represent, as the problem says in your book, number of cell sites where electronic communications equipment is placed in a cellular network. So the first part says find number of cell sites in the years 1985, 2000, and 2006. Also, with a lot of these problems, this is a common thing. Please don't. This is an easy mistake to make. They make, in this case, 1985 t equal to 5. Okay, so 1980 is year 0 in this case. Okay, so what we're going to be doing for define what is it 1985, you're going to put t equal to 5 in, put t equal to 20 in, t equal to 26. Okay, you're putting all those values into this function. You may use your graphing calculator. I don't expect you to do this by your head. And your answers would be for 1985, you get 115.1 0.25, but you can't have 0.25 cells, so we 715. And for 2000, you had 90,880. And then for a t equal 26, we have 199,043. Okay. The other part of the question, if you are in your book, wants to know when the output will reach 235,000 total. Okay, so that's going to be your y, right? So we want to know what year that's going to happen. So algebraically, we can solve this. And when we do that algebraically, we need to multiply both sides by the denominator and then isolate t. Okay, so when we multiply both sides by the denominator, we get 235,000 plus 235,000 times 1,950. We get a really big number, and that really big number is 458,250,000 equals, oh, I forgot about the e. Base e to the power of negative 0.355 t equals 237,101. So we can subtract both sides by 235,000. Getting us 2,101 equals left side. And then we're going to divide both sides by 458,250,000. And then on the next slide, I will show you what happened next. So we get to this, and then you L on both sides, and you're going to get negative 0.355 t equals negative 12.29 approximately. Divide both sides by negative 0.355. And you're going to get t is equal to approximately 34.63, which means t equals 35. The answer is not 35 though, right? Because we need to add it to 1980. So in that case, it'll be 2015 is your answer. All right, I appreciate watching, and we'll see you in class. Bye-bye.